Very good morning. Welcome to fourth week lectures. This week we will concentrate on multivariate normal distribution. Today we discuss the basics of multivariate normal distribution, and then we will show you bivariate normal density function. Let us see next.
Multivariate normal distribution. Last class we have seen the univariate normal distribution. This is the formula. If x is a random variable, then 2 pi sigma square e to the power minus half x minus mu by sigma square minus infinite less than x less than plus infinite. So, the PDF multivariate normal PDF is characterized by mu and sigma. Mu and sigma, that is a population parameter. Okay. We want the counterpart of it in the multivariate domain when x, that univariate x is converted to capital X, which is your x1, x2, xp, and univariate mu is no longer univariate, it will be a very mean vector mu1, mu2, mu p, and similarly univariate sigma square will no longer be univariate, it will be a multivariate covariance matrix. P cross P. So, that means we want something by multivariate normal distribution, we want something which is f x in terms of n variable number p and mean vector and covariance matrix. How do we go about it and how to do it? That is the discussion today. So, today we will discuss bivariate normal density function, multivariate normal density function, and properties of multivariate normal density function, and if time permits we will go for statistical distance and constant density contours. So, the univariate PDF is this. You want to visualize its multivariate counterpart. So, let us consider a bivariate case. You see this slide, in this slide you see that there are two variable x1 and x2 and probability density, that is joint density, that f x1 and x2, x1 and x2. Okay. So, this is what is given in figure. So, you see that you are getting a bell shape, but in 3 dimension you are getting, because there are first 2 dimension for the 2 variable values and third dimension is the density values. And if you take one more dimension, it is difficult, you cannot visualize. Getting me? Suppose there are 3 variables with density, we cannot visualize pictorially. Now, as I told you, our objective of the first part of today's lecture is we want to develop this. This is our objective. This one is our objective. So, in order to do so, we will follow a systematic but simple path. Okay. Suppose you think that you have 2 variables x1 and x2, which we are saying a bivariate case. So, our x is x1 and x2, that is y, and my mu is that mean vector mu1 and mu2, and your covariance matrix will be 2 by 2, sigma 1 1, sigma 1 2, sigma 1 2, sigma 2 2. I hope that there is no problem with you in this one nomenclature. So, we assume something here. You see the slide here. In the slide, you see the top figure, that here is a scatter plot. Now, what you can say about the two variables x1 and x2, seeing the scatter plot? Are they correlated or there is no correlation? Is it something like a circle you are getting or ellipse? There is no pattern. So, you see that it is an ellipse type of thing, but there is no correlation. So, we want to simplify our derivation without correlation. So, that means what I mean to say, our sigma 1 2 is 0 or rho 1 2 is 0. If there is no correlation, then what will be the joint density? Suppose x1 and x2, multiplication of the marginal density of the two. So, x1 cross x2. Okay. Now, all of us know that f x equal to 1 by root over 2 pi sigma 1 square as it is x1 e to the power minus of x1 minus mu 1 by sigma 1 square. Then similarly, for f x2 also, that is the second variable, you can write 2 pi sigma 2 square e to the power minus of x2 minus mu 2 by sigma 2 square. We can write this, and definitely here xj less than greater than minus infinitive to less than minus infinitive, j equal to 1 2, two variables you have taken. So, if I multiply this, what we are getting? We are getting like this 1 by, there is one quantity called 2 pi. So, 2 pi you are getting 2 by 2, 2 pi into 2 pi square root 2 by 2. Then another one, what you are getting, sigma 1 square and sigma 2 square, also sigma 1 square sigma 2 square to the power half you are getting here. Yes or no? And then I am coming to the exponent part, e to the power minus half, and all of us know that e to the power a into e to the power b equal to e to the power a plus b. So, we can write this one like this, x1 minus mu 1 by sigma 1 square plus x2 minus mu 2 by sigma 2 square. We can write this. So, essentially what is happening here, that in when I go for that univariate normal or bivariate normal with no dependent structure, you are having two component in the density function. One is the constant part, another one is the exponent part. Two part is there. One part is component, that is the constant, another part is the exponent, means e to the power something. And when you are making the joint distribution here also, you are having also two part, this and this. The general structure for the multivariate normal distribution univariate that remains same. What is the difference? Difference will come in the to the components, the values will be different. So, we found out that if x1 and x2 are independent, then our structure is like this. Okay. Now, let us see that we want to derive this constant part as well as exponent part from the population parameter, that is what we have mu equal to mu 1 into mu 2 mu equal to mu 1 mu 2, not mu 1 mu 2, mu 1 mu 2, and we have sigma is sigma 1 1, sigma 1 2, sigma 1 2, sigma 2 2. This one you can write now, sigma 1 1 equal to sigma 1 square, sigma 1 2, sigma 1 2, sigma 2 square. Okay. So, if I make something like this, determinant of sigma. What is the determinant of sigma? Here sigma 1 square, sigma 1 2, sigma 1 2, sigma 2 square, its determinant. And you know that determinant will be this cross this minus this cross this. So, this one is sigma 1 square, sigma 2 square minus sigma 1 2 square, correct. Now, you see that what we have assumed in the earlier demonstration, we say sigma 1 2 equal to 0. Just for the sake of simplicity, we have taken like this, sigma 1 2 equal to 0. So, if sigma 1 2 equal to 0, then determinant of sigma is nothing but sigma 1 square, sigma 2 square. So, if I make square root of this, then this is the determinant or square root of the determinant. And if this is the case, then the constant part, what is the in case of our independent bivariate density function, we found out that constant part is 2 pi 2 by 2 sigma 1 square sigma 2 square to the power half. Now, this I can write like this, 2 pi 2 by 2 determinant of covariance matrix to the power half. Okay. Now, suppose you have one more variable. That means, suppose you have taken 3 variables now, like x is x1 2, x2 and x3, and you have also consider that your sigma is sigma 1 square 0 0 0, sigma 2 square 0 0 0, sigma 3 square. What we are assuming? We are assuming that all the variables are independent. Then what will happen again? F x1, x2, x3, it will be f x1 into f x2 into f x3. So, in the similar way you multiply, ultimately your constant term will be 1 by 2 pi, now 3 variables are there, by 2, then sigma 1 square, sigma 2 square, sigma 3 square to the power half. You see, if you take determinant here, what are you getting here? It will be sigma 1 square, sigma 2 square, sigma 3 square. So, that means determinant to the power half is sigma 1 square, sigma 2 square, sigma 3 square to the power half, to the power half. So, if you now increase it to p variables, so ultimately your sigma, that dimension will change, and sigma to the power half will take care of one part of the constant. So, if I go by p variable now, my constant will become like this, 1 by, you see that when there are 2 variables, it is 2 by 2. When there are 3 variables, 2 pi to the power 3 by 2. So, when there are p variable, it will be p by 2, and whether it is 2 variable or 3 variable or p variable case, ultimately this quantity will be replaced by determinant of covariance matrix to the power half. So, with one assumption here, that we are considering independent variables, we proved this is the case. Now, what will happen to your constant exponent term? So, in 2 variable case, we found out that the exponent term x1 minus mu 1 by sigma 1 square plus x2 minus mu 2 by sigma 2 square. So, we say this is the exponent term. This is the exponent term, this portion is exponent term. So, it is x, you see that x 1 minus mu 1, that is mean subtracted, divided by its standard deviation, that square. So, now create one, suppose x minus mu transpose, no, I'll explain from the univariate case, that will be better. So, univariate case f x 1 by root over 2 pi sigma square e to the power minus of x minus mu by, this is the case you have seen. Now, take the exponent one. So, your exponent is minus half, I am writing x minus mu sigma square to the power minus 1 x minus mu. Is it not this one? Is it not minus of x minus mu by sigma square? You see, x minus half is there, minus half, x minus mu, x minus mu square divided by sigma square. So, sigma to the power inverse. Now, if you go for the multivariate case, what will happen? Your x is replaced by capital X, mu is replaced by bold mu, sigma square will be replaced by sigma, correct. Now, in matrix multiplication, what will be the square? Transpose that matrix, x transpose x, that is the square term. So, we are basically making here square. So, we want this. So, that is why what I mean to say, in multivariate domain the exponent can be written like this, x minus mu transpose sigma square is replaced by capital sigma to the power minus 1 x minus mu. That from univariate normal distribution, we have taken the exponent part, and we are saying that if we go in same manner to the multivariate part, our resultant quantity will be this for the exponent. Is it so? Can we prove now? Can we do like the same thing for x equal to x1 and x2 two variable case, mu equal to mu1 and mu2, and sigma equal to, we have taken already sigma 1 square 0 0 sigma 2 square, because we are independent case we want to prove first, because we know under this condition what will be the distribution multivariate normal density function, that is known. So, then you write down minus half. So, x minus mu transpose. So, that means this is x1 minus mu 1, x2 minus mu 2, because x minus mu is x1 minus mu 1, x2 minus mu 2, 2 cross 1, it will be 1 cross 2. Okay. Now, your what do you want? Sigma 1 square 0 0 sigma 2 square, this inverse, then what you, so that is 2 cross 2, then x1 minus mu 1, x2 minus mu 2, this is your 2 cross 1. So, what is the resultant quantity? 1 cross 2, 2 cross 2, 2 cross 1, it is a 1 cross 1. This will give you 1 cross 2, this will give you 1 cross 1. It is a density that exponential to the power this constant value, you will be getting some value, density will be calculated. Okay. Now, what is the inverse? How do you calculate the inverse? Suppose if A is a matrix like this, A11, A12, A21, A22, how do you compute the inverse? 1 by adjoint by determinant. So, A inverse, it is adjoint of A by determinant of A. Now, adjoint is the transpose of the cofactors. Adjoint is transpose of cofactor of A divided by determinant of A. So, if this is the case, our A is nothing but this one, sigma 1 square 0 0 sigma 2 square, that is what is our sigma. Now, determinant already we have seen that determinant is sigma 1 square and sigma 2 square, multiplied by these two. Now, what will be the cofactor of this? Cofactor is, if you suppose I want to know cofactor of sigma here. Here suppose in A case you see cofactor means, suppose you want to see the cofactor of this, then you have to cross this the corresponding row and column. What is left, that is the cofactor, but the sign conversion will be there. So, that means cofactor means, so for A I j the cofactor will be minus 1 I plus j, correct, in the remaining portion, whatever the remaining portion, remaining part of the matrix, that will be the case. As we have taken 2 by 2 cross, so ultimately what will happen, one row and one column crossed means only one item will left. So, it is our case is easier. Then cofactor of this we can write, first one is minus 1 to the power 1 plus 1, that is 1 plus 1. Then what is remaining here, sigma 2 square, suppose you cross this and this, sigma 2 square will be there, and see it is 0 and it will be also 0, and sigma 1 square will be this. So, our cofactor is sigma 2 square 0 0 sigma 1 square. What will be its transpose? Same, because these two elements are 0. So, now transpose of cofactor of sigma this is again coming the same thing, because row and column interchange, it is symmetry 1 0 0 sigma 1 square. Then what is my inverse? Inverse is that is the cofactors, mean 1 by determinant you write down first, sigma 1 square and sigma 2 square, that is the determinant, sigma 2 square 0 0 sigma 1 square. Okay. Now, calculate this one. My calculation is minus half our x 1 minus mu 1, x 2 minus mu 2, then inverse is coming like this, 1 by sigma 1 square sigma 2 square, sigma 2 square 0 0 sigma 1 square, then multiplied by x 1 minus mu 1 and x 2 minus mu 2. Suppose if I do this portion first, what you will get? You will get minus half x 1 minus mu 1, x 2 minus mu 2, 1 by sigma 1 square sigma 2 square. This is 2 cross 2, this is 2 cross 1, you will be getting 2 cross 1. This into this plus this into this. So, it is basically sigma 2 square x 1 minus mu 1, then this into this plus 0, then 0 plus again sigma 1 square x 2 minus mu 2. Now, let me bring this one this side, later on we will manipulate, sigma 1 square sigma 2 square. So, if you multiply this 1 cross 2 and 2 cross 1, you will be getting 1 cross 1. So, this into this plus this into this, you see what is happening, sigma 2 square x 1 minus mu 1 square, because x 1 minus mu 1 x 1 minus mu 1, plus sigma 1 square x 2 minus mu 2 square. So, if you divide these two by sigma 1 square sigma 2 square, what you will get, what you will be getting? You will be getting like this, minus half, then it will be sigma 1 minus mu 1 by sigma 1 square plus x 2 minus mu 2 by, correct, x 1 minus mu 1 by sigma 1 square, this one. And you have seen that we have found out earlier also, this is f x 1 cross f x 2, this we found out like this. This one only you found out. This one you found out, you just check. I am showing that earlier when we have multiplied the 2, what we got here, 1 by 2 pi 2 pi to the power 2 by 2 sigma 1 square sigma 2 square half, then minus 1 by 2 x 1 minus mu 1 by sigma 1 square, this one, and here what are you getting? Here same thing you are getting. So, what I mean to say, although this is not a derivation, this is the other way proof, that what we are saying, that means I can write for a bivariate case, I can write my bivariate normal distribution like this. This is the case. You can write like this. Okay. But if, and it is true for multivariate case also, then what will happen ultimately? Multivariate case x 1, x 2, x p, then it will be 2 pi to the power p by 2 determinant of this, then e to the power minus of x minus mu transpose, this is the case, and you have to write minus infinite x j infinite, j equal to 1 to p. This is our multivariate normal distribution. We say multivariate normal density function defined. Okay.